Welcome to today's adventure, SparkML and the missing fast inference. So what is SparkML and missing fast inference? Well, if you've used Spark, Apache Spark, machine learning at all, you've probably noticed that it's great for training models over large amounts of data, and it's also great for using those models to do prediction over large amounts of data. But if you have a use case where you need to do fast inference on a small amount of data, like maybe you have a visit from a customer to your website and you have only 10 milliseconds to make some decision about what to do, Spark doesn't really have native support for doing that. So it's easy to run into problems here, and there's very little written about this in the Spark books and documentation. So it's kind of a known issue, but you may not have heard about it so much before. Today let's look at a free and open source library that helps us deal with this problem. My name is Adam Brindell. I'm an engineer, consultant, and instructor who works on Apache Spark and big data systems quite a bit. I've got some bio information up here. You're welcome to connect to me on LinkedIn, and we can talk about your fun Spark projects. There's a link to this notebook itself that I'm demoing from here today on the YouTube notes, so you can import this notebook and try this out for yourself. And get a hold of all of the live links afterwards. So before we dive into the demo for fixing the problem, let's clarify what we mean here a little bit. So in the machine learning world, we often talk about a training phase versus an inference phase with our models. Training phase is about building the model from data, evaluating models, tuning models, feature engineering, all of that fun stuff. For today, I'm assuming that you're already familiar with how to train models using Spark. If you're totally new to SparkML and you want to learn about how to use SparkML to build and train your models, I have links here to my class from Spark Summit Europe 2016, where I taught the one-day data science with Apache Spark class, and we cover all of the important pieces of the API for building ML models. So you can go back and maybe take a look at that. For today, I'm going to assume that you already either have done that or you do a lot of this model building and you're familiar with that. And now we want to look at the deployment or inference or prediction part of the application. So within inference, there's kind of two categories. Bulk or batch inference, where we have a large number of data records, maybe all of a company's customers, and we want to make a prediction like maybe how much they're worth or what sort of ads to show them. And we don't need results right away. We just need them, sooner or later in some reasonable amount of time. The other case is low latency inference. In low latency inference, we have a small number of records, maybe just the one customer, and we need very fast results. Maybe we have 50 milliseconds that we're allowed or 20 milliseconds to make a decision about the best product to offer that customer right now. So SparkML is currently not designed to be able to handle this low latency inference, right? It theoretically could with some re-architecture, and there's been some discussion about that. So in the future, this might change. But for now, when we go to make predictions on a data frame of records using SparkML, Spark schedules jobs. Those jobs are scheduled like every other Spark distributed job. And that introduces a certain distributed scheduling tax. Normally in Spark, that tax is paid for by the benefit of working over huge amounts of data, so that tax isn't very expensive per record. But when you're only predicting for 1 or 2 or 10 records, that tax has a big impact. And so it makes it nearly impossible to use Spark directly to do low latency inference. Now before we look at a solution, just to be even more clear, let's mention a couple of examples. So for batch inference, right now it's holiday shopping season in a lot of Western countries. That means tons and tons of emails offering deals. The smart companies use machine learning models to send out personalized offers, and they can run these maybe at night or offline because they're just going to send out this email, over a period of hours to all of their customers. So if it takes them 4 hours to make predictions for their customer base, or even 4 minutes, it doesn't really matter, right? Because we're getting this asynchronously via email later. On the other side of things, we have low latency inference. An example there might be deciding whether a purchase is likely fraudulent. So someone goes to buy concert tickets with a credit card, And you might have 5 or 10 or 20 milliseconds to decide, do we want to approve this purchase? And we're going to give up those seats and we're going to, charge this credit card. Or are we concerned enough that maybe we're going to decline this because it's not a kosher transaction? So that's a classic low latency inference example. Other low latency cases include things like bot detection or online ad auctions. And most enterprises doing lots of different things with machine learning have both cases. So it's not that you live in one case or the other. Most companies have some uses for both. So you need a solution for both. Okay, so how do we fix this Spark issue? It's really not too crazy. Once we realize that Spark can't handle this low latency inference but does everything else pretty well, we're going to build our models with Spark. We'll do our batch inference in Spark, that's fine. For the low latency cases, we're going to export the model from Spark. We're going to load that model into some other runtime and integrate that into our application architecture. So a couple of footnotes for this. We probably want to export the whole SparkML pipeline. The pipeline includes feature engineering, things like scaling and one-hot encoding, and we want to be able to do the same pre-processing steps to our real runtime data vectors as we did with our training and test data vectors. So we want to, in order to preserve the semantics of the whole pipeline, we kind of need to reproduce that whole pipeline logic somewhere else outside of Spark. We can't use pipeline.save that's built into Spark because it produces a proprietary format that we can't really use with other tools. And if you've used the older versions of SparkML, you may know that, or MLlib, you may know that some of those older models could export to PMML, and that functionality is not supported in the new API either. So this is why we kind of need something totally separate to work with us here. Then we'll take that, we'll load that somewhere else, expose it by some kind of simple service, and now we can make fast predictions. So for today's demo, we're going to look at a great open source project called MLeap. I've got links here to the GitHub code and the documentation as well. And MLeap allows us to do exactly what we want here, to export pipelines, run them somewhere else in any kind of Java or Scala environment very easily. And in the future, it will also have support for scikit-learn and TensorFlow pipelines in addition to Spark. So it may be possibly a one-stop shop for doing your inference. Okay, so let's dive in here. First thing I'm going to do is build a Spark pipeline model. Again, I'm assuming that you're familiar with building and training models in Spark already, so I'm not going to explain all of this API code. This is a model over the diamonds dataset that comes with R. So we're learning how to predict the price of a diamond from its properties, things like its carat weight, its quality, and other measurements. And when this model is finished training, let's see, it's still kind of running here. Give it another minute or so. We will have a pipeline model, and here we go. Now I have a pipeline model called GBT model. Just as a sanity check, I want to make sure that it works. So I'm going to do a transform on the test set to make predictions. All right, so here's my data frame with the prediction column. And again, I know I'm going fairly quickly here, but this isn't the focus of today's tutorial. We want to learn how to run this somewhere else once we've got it built. We'll run a little regression evaluator here to see how we did statistically. Our RMSE is $710 and change, which is pretty good. And here, let's see what would happen if we did have a single record and we wanted to make a prediction. So just as kind of a baseline. If I take my test data frame and I put limit 1 on it, so I'm saying I want to represent only the first record in this data frame, I can predict on that by calling .transform. And then I can pull the resulting row back into Python with .first, and we can see the results. So here we've got some properties of the diamond and a prediction of $580. And notice this took about 1 second to run. So I'll run this a couple more times. It'll speed up a little bit. Now that was even slower. There's a little quicker. If you play with this, what you'll note is that you can't really get below a few hundred milliseconds. So we can put this on a faster server, but But in general, you're not going to be able to do this underneath 100 or 200 milliseconds, even though we're in local mode. So there is no actual network communication. We're just in a single JVM. So again, Spark is great for lots of data and lots of time, or lots of data and a moderate amount of time, but it's not great for a tiny bit of data. Right? That's the problem here, is we're spending way too long doing this one prediction. Okay, so let's go and take a look at MLeap. So far so good. We're just doing standard SparkML. Now we want to export our model for use with MLeap. So to prepare for this demo, I added two libraries to my instance here. MLeap Spark, which is kind of the core MLeap stuff for Spark, like it sounds. And MLeap from PipelineAI, which is the PySpark helpers that go with it. Because I wanted to do this ML demo using Python, so I brought both of those in. I've got MLeap on my class path. You can get those jars from Maven or however else you'd like to do it. And then I've got MLeap, which you can pip install. So let's go and do some imports here. I'm going to delete some temporary files in order to make this notebook rerunnable. So that way you and I can both run this more than once. And now here's the special line, gbtmodel.serialize to bundle. So that's a helper that gets added in from the MLeap code. And we're going to save this, in this case, as a zip file. And over here on the right, notice that I'm passing a data frame, predictions.limit0. So predictions was the data frame with the actual predictions that we did above. But I'm not submitting any rows here. I'm putting limit 0 on here so that I pass a data frame that references no rows. So why would I do that? What's the point of that? Well, in the SparkML system, there is metadata which is occasionally stored in the data frame itself. So we all know the data frame has column names and column types. It turns out that you can also stash interesting and useful metadata in the data frame. And so to preserve the semantics of the pipeline, it's sometimes necessary to have access to that metadata. An example is encoding strings with a string indexer. You may have seen examples where Spark can then convert the other way, from the numeric index back to the original string. Right? That's a pretty amazing magic trick until you realize that the lookup map is actually hidden in metadata on the data frame, and that's how that step works. So without that metadata, there's no way we could get the pipeline to reproduce the same semantics outside of Spark. So I'm going to pass predictions, but no rows. So we just get the metadata, and let's get this thing running. And there we go. Hopefully we have a file now in /temp called diamonds.zip. I want to get this out of Databricks and move it into a VM that I'm playing with on my desktop. So I'm going to copy it over to /dbfs/filestore. And the file store path under dbfs allows me to retrieve this file via HTTP. So we can just make sure it's in there. I've got about 35K of data. And then to retrieve this to my desktop, what I'm going to do is come to this URL. So my Databricks preamble and then /files, which maps to that special file store path, and then diamonds.zip. So Chrome just downloaded that file to my machine. We'll need that in a few minutes, but not quite yet. So the next thing we want to do is switch over to our Linux VM, and we want to run an MLeap Inference service and load our model into it. So again, MLeap is open source. Java, Scala, and other tools, you can run it inside of your own Java or Scala applications. For our demo today, I'm going to use a sub-project called MLeap Serving, which is kind of a fully baked REST server that's designed to ingest these models and then do fast service via a REST interface. And the MLeap project has a nice Docker image that I can use, so I don't even need to compile this all myself. I'm actually going to install it using Docker. So what I've got here are some command lines that I'm going to use. Don't run these in Databricks, they won't really work, but I put them in the notebook so that you'll have access to them. If you'd like to play with this on your own, you won't have to kind of squint at the screen and try to type what I'm typing if you want to try this out. Okay, so I've got a Linux VM here, just a simple Ubuntu machine. What I've done is I've installed Docker on it. And in order to save some time, I already installed the MLeap Docker serving image. So if I wanted to install it, that would look something like this. I'm actually not going to run that command because it takes a few minutes to run. But if I do a Docker images, you can see I've already got this guy sitting here. So what I'm going to do is start it up. So that's going to be this Docker run command. So we're going to expose a port, and we're also going to map a directory so that we can put our model somewhere that the container or the code inside the container can find it. So I've already taken the file that I got from Databricks and Spark with the exported pipeline bundle. I brought it over here into my Linux VM. So currently it's sitting right here in the home directory. I'm going to go ahead and move this guy or copy it over to temp/models. And then I'm going to make a REST call in order to load that into the server. That's going to look something like this. So we're going to do a put. We're going to point to models/diamonds.zip. That's the in-container version of the path we just put our model at. Okay, so that looks like it succeeded. So, well, what do we do now? Now we've got this server running, maybe, and we've got a model in it, maybe. Well, we need some data to predict with. So now I'm going to flip back over to Spark, and we'll go ahead and come up with some records to try out here. So let me just switch over. All right, so now we have our MLeap running our model, and what we'd like to do is move some data from here into there so we can try it out. Now, in order to maintain the whole semantics of the pipeline, MLeap uses a local kind of imitation data frame called a leap frame. There are various ways to represent a leap frame. For today, we'll just use JSON. It's not the most compact, but it's very clear. So let's take a small amount of records, because remember, the whole point here is to do fast inference on small numbers of records. And then let's go and make a leap frame. So I'm going to take my test data frame that came from the training test split earlier. I'm going to drop the price column, because that's the thing we're trying to predict, and I'm going to downsample it to a small number of records. Maybe 10 or 20. Okay, so it looks like in this case I got 24 records. And we can see what those look like. So here are 24 diamonds. Now, what is our JSON leap frame going to look like? Well, here I made kind of a little mock leap frame so you can see what the format looks like. It's got a collection of rows and an object called a schema. So rows are exactly what it sounds like. It's a JSON list of lists of fields. In this case, I have 2 rows. And then there's a schema, which is which contains a field called fields, and that contains a list of items which have a type and a name. So that way our leap frame is kind of self-describing. So how do we get our data from Spark into this leap frame format? Well, in this case, what I'm going to do is I'm just going to use a couple of list comprehensions to build some Python objects that I can JSONize. In real life, you probably wouldn't have the data that you're needing in Spark to begin with. You probably would have it somewhere else. So this is not necessarily a process you'd actually have to do, but it is useful to be able to do it. So we're just going to take our rows and we're going to make a bunch of lists of those. So we now have a list of lists. So these are the rows. Then we're going to go and dump the schema for our data frame here. So what I'm doing is I'm using the .schema property of the data frame and then walking through there and pulling out the name of each column and the type. And that's going to give me a Python dictionary that looks something like this. Right, so this is the schema of what's going to be my leap frame. So now I have a bunch of rows and I've got the schema. We can put those into a Python dict like this. So the leap frame dict looks like this. Schema contains fields pointing to schema and then rows pointing to rows. And we can just use JSON and dump string to get it out like this. So again, you probably wouldn't need to do this in your real application, but here we want to see kind of how to do the complete end-to-end and make sure that it's all behaving the way we want. So I'm going to use this data from Spark. We're going to test it. We'll make sure it's doing the right stuff. So, okay, what I'm going to do is just flip over here. I'm going to use classic clipboard integration. I'm going to copy and paste this string over into my Linux VM. So I'll come in here and we'll go gedit demo.json. Let's see, do I want to call this demo? I'll call it test.json. Test.json. And I'm just going to come in here and paste this in. Right, so this is just the exact string we had a moment ago. So I'm going to save that. Okay. Okay, so now comes the really fun part. We're going to take our small data frame, our leap frame, I should say, and we're going to fire it at our model, and we're going to make some predictions. So how do we do that? Well, it's just another REST call, because that's the whole point here. So it's going to look like this. We're going to do a post. We're going to have the right JSON content types. We're going to point to our test.json file. And we're going to send that to /transform. And there we go. So now we've got, that happened so fast, I almost can't even see it. So that is our predictions. You can see that actually what comes back, if I rewind here just a little bit, the result of that post looks like we've got one or two warnings, and then we've got some schema information about the output data frame or leap frame. I keep saying data frame, but it is a leap frame. And then we've got the actual vectors, and this last value here, so for example, this number right here, those are the predictions. Okay, so now the next thing we want to do is make sure, like, are we actually getting the same values we would have gotten from Spark? So getting fast answers that are wrong is not very helpful. Let's just verify that these are the same as the results from Spark. So I'm going to flip back over again. So let's do a predict on our small test data frame over here in Spark and see if we get the same results. So here are our predictions in Spark: 681, 638, 757. Actually, maybe I can move this to the side and maybe we can see these at the same time. And there we go. So you can see right here, 681, 638. It's the same order. And we can work our way down. So we've got the exact same math and the exact same logic that we had in Spark, only now we're able to do it really fast in any Java or Scala application we want, or in this case, maybe not even with an application, just using MLeap serving, much quicker. So let me kind of swap my windows around here. And we'll go back to here. So, okay, well, one last thing. So how long is this taking? Well, again, you can't really do serious benchmarking when everything is all in virtual machines and Docker and on a single machine. So this is not a real benchmark, but we can get some orders of magnitude maybe. So I've made a separate file here, and I'll show you it. Cat, I have to be in the right window for this. Cat, one back. So this is a leap frame with a single record called onerec.json. And if you look at that, you'll see that it has one row. So the rows collection has just this one diamond in the original format. And then it has the schema object. So if I had to make a very fast prediction for one record, I might have some chunk of data that looks like this, and I might want to know how long it takes. So I'm going to use curl, and I'm going to use the little total time magic. So looks like I have a little typo in here. Let's go fix this up. I don't know how that got in there, but I will fix it right now. Okay, so we're going to do a post. We're going to fire onerec.json into our server, and we're going to print out the time total. And you can see that we got, let's see, that was 18 milliseconds. And if we run this a couple more times, we can just see, is it generally in that vicinity? And it looks like it is, right? So 13, 18, 10 milliseconds. And again, this doesn't, it doesn't serve as a permanent benchmark, but it does give us an idea that we're in the right neighborhood here, right? We're now able to do local inference that doesn't involve distributed scheduling. We're getting results out in a very small number of milliseconds. We're getting the same semantics that our pipeline had, including the string indexing and so on. We're getting the same math. And now we've got a nice environment we can use for all of this. So, okay, excellent. So let's flip back here and we can wrap up. So is MLeap the only way to do this? And the answer is no. The architecture pattern here is the most important thing. We need to understand what Spark can and can't do. And specifically, we need to understand that Spark cannot do this kind of low latency inference that we need in its current form. Once we understand that, we can look for other tools to work together with Spark in our architecture. Right? MLeap is a really nice one, but is not the only one. Some other things you might want to look at. DBML Local. This is a tool that Databricks is building. It may handle some of these cases. It's kind of very early days for DBML Local, but if you're a Databricks customer, you might want to talk to them about that. It's in Maven, so you can go in and pull down the code for this if you want to kind of see the latest state. Let's see, what else? JPMML and Openscoring.io. So this is a company and a set of open source projects that support export and inference via the PMML standard. So this is a really nice industry standard format. Now, if you want to work with those tools, you may need to negotiate some custom licensing because they use an AGPL license, which a lot of companies can't use. So just a little caveat with that, but that's kind of another approach. A kind of all-in-one platform is something called PipelineAI. That's an award-winning open source-based platform that does management and deployment of Spark or TensorFlow models, including kind of full lifecycle deployment, monitoring, A/B testing, model migration. So if you need kind of a bigger, if you're interested in maybe an open source, bigger platform for managing your inference, that might be something to look at. So lots of ways to do this, but again, most important thing is realize where Spark is great, realize where we need to add additional tools to Spark in order to get a successful architecture. You can try this stuff out. MLeap is constantly evolving and it's kind of under active development. So within a couple of months, it's possible that the APIs or the versions may be a little different than what we got here today. But I hope this is really useful. This is a major question that comes up constantly in Spark classes and other work that I do is how do I do this inference and why doesn't my inference work? I hope we've dealt with that here successfully today and best of luck.